So I will be talking about reasoning in the ASPIC plus formalism with answer set programming. Argumentation is a vibrant area in artificial intelligence research, and it has several avenues for applications such as law, medicine, e-politics, and basically any field where you want to draw conclusions from inconsistent or incomplete knowledge bases. And most of the algorithmic approaches for argumentation focus on abstract rather than structured argumentation. In structured argumentation, the formalisms are more involved because the structure of arguments is made explicit as opposed to just having atomic arguments. And also the complexity of reasoning in structured argumentation is often less understood, and there are fewer implemented reasoning systems for structured argumentation compared to abstract argumentation. Recently, we have developed an efficient ASP-based system for reasoning in a structured argumentation formalism called assumption-based argumentation. And this has motivated us to extend this approach to another formalism, namely ASPIC plus. So we focus on this instantiation of ASPIC plus, where we can have strict and defeasible rules with atomic components. So the rules are composed of atoms. We also allow for asymmetric negation, but no preferences for now. Our contributions in this work have been to provide complexity results for acceptance problems in this instantiation of ASPIC plus under various semantics, as well as develop a new computational approach for reasoning in ASPIC plus, namely encoding ASPIC plus reasoning as answer set programming. This approach covers various semantics and reasoning modes, namely credulous and skeptical acceptance and extension enumeration. And we also empirically evaluated this approach and showed that it scales up to instances with thousands of atoms, meaning that this approach is actually very usable in practice. So I'll give brief background on ASPIC plus. So in ASPIC plus, we have an argumentation theory which consists of a language of atoms, and then we can divide the elements of the argumentation theory into strict and defeasible parts. So in the strict parts, we have axioms, which are basically facts. So things that we know to be always true, we cannot dispute them. And similarly, strict rules are rules that are always applicable. In contrast, premises are things that we assume to be true as long as we don't have any good evidence to the contrary. And defeasible rules are rules that are applicable as long as we don't have a reason to think that they are not applicable in this situation. And this divide is reflected in the fact that all atoms in an argumentation theory, apart from the strict ones, can have contraries. And then attacks are defined based on these contraries. And the reason in ASPIC plus, you build an abstract argumentation framework, you build all the arguments, and then evaluate this framework with standard AF semantics. And I'll give you an example of how this works. So this is an AT, and we have all kinds of atoms here. So we have the axioms C and A in the solid blocks here, and then a premise B in the dashed block. And you can see that, for example, B is attacked by W. And we have strict rule here. From B, you can derive X. And another rule, but this time defeasible, you can derive Y from C. And this defeasible rule, the contrary of this rule is Z. So this argument containing Z, namely A7, attacks this argument containing this defeasible rule, namely A4. And so we have 7 arguments in total in this once we build the AF. And the AF looks like this, and we can see that indeed A7 attacks A4 in this abstract argumentation framework built from this AT. And so once you have the abstract argumentation framework, then you use standard AF semantics to obtain the reasoning solutions. The semantics we consider in this work are all very central. These 4 semantics: admissible, stable, complete, and preferred semantics. And just briefly, admissible extension is a set of arguments that is conflict-free and counters all incoming attacks. And a stable extension is conflict-free set of arguments that attacks all other arguments. And a complete extension is a set of arguments that's admissible and contains every argument that this set defends. And preferred extension is a set of arguments that's subset maximally admissible. Now onto our contributions in this work. So in terms of complexity results, we consider the problems of credulous and skeptical acceptance. So an atom is credulously accepted if it's derivable in some extension sanctioned by the given semantics. And an atom is skeptically accepted if it's derivable in every extension. And the results are like this. So our contribution are the completeness results. The hardness results follow from earlier reductions from ABA and AF. So credulous reasoning under all these four semantics we consider is NP complete. And skeptical reasoning under stable semantics is co-NP complete, and skeptical reasoning under preferred semantics is pi P2 complete. So on the second level of the polynomial hierarchy. And in terms of actually computing these solutions, we have developed an answer set programming approach. So answer set programming is a declarative programming paradigm with very efficient solvers, and it is already extensively used for reasoning in abstract argumentation. As I mentioned before, we recently showed that the ASP can be successfully used for structured argumentation, namely for assumption-based argumentation. And now we are extending this approach to ASPIC+. And encoding ASPIC+ reasoning directly as ASP has several benefits. Firstly, this approach is quite modular, so the various semantics share a large part of the encodings. And once you have the bulk of the encoding, then obtaining these other semantics is actually quite straightforward. So the encoding itself is not trivial. It's quite involved, but once we have the bulk, then the rest of the semantics are relatively easy to encode, at least for these semantics we have. And this approach supports or gives support readily for credulous and skeptical reasoning and extension enumeration. And maybe the biggest advantage is that we don't need to do the actual AF translation. So we don't need to translate the argumentation theories into AFs. And this translation might be very costly because you might have a large number of arguments. And so you'll have to, in the standard way, you would have to build this AF, build all these arguments, and then after that, you still have to solve the problem in the resulting AF. So to avoid this sort of two-step process, we characterize the semantics of ASPIC+ directly in terms of the defeasible parts of the argumentation theory. So we define an assumption, which is a pair PD, where P is a subset of the premises and D a subset of the defeasible rules. And then based on this definition, we define attack, defense, and semantics. You'll have to see the paper for details on those, but then we showed that for all these four semantics we consider, there is actually a correspondence between the standard AF sort of extension definition of ASPIC+ semantics and this new assumption definition of the semantics. And this means that we can answer credulous and skeptical queries using this new assumption definition of the semantics. And so in practice, we did this approach with ASP, where you guess a subset of the divisible parts, check if they characterize an extension, and then we obtain the answer to the given reasoning problem. So you can use queries in ASP to see if an atom is contained in the solution, for example. And empirically, we evaluated this approach. And here, by atom we mean a member of the language excluding names for the rules. So we tested the effect of varying the number of atoms in an instance or in the instances and the proportion of atoms that are axioms. And then we have the rest of the parameters which depend on the number of atoms. So the details on these are not so important, but just some number of the rules are divisible and some atoms are premises and so on. And here's a plot showing what we found. So on the x-axis we have the number of atoms, and on the y-axis the mean running time over the instances with the given number of atoms, with a 600-second timeout, and each data point is 25 instances. And then the 4 different percentages are the proportion of atoms that are axioms. So we varied it from 0.5% to 10%, and this is under admissible semantics. So you can see that the more you have axioms, the easier it is to solve these instances. So when you have 10% axioms, it's actually quite easy to solve even with more than 5,000 atoms in the instances. And this makes sense because as you increase the proportion of axioms, you decrease the uncertainty in the instance, and so you limit the search space. And here is some more tasks. So this table shows the results for Krejcir's reasoning under admissible, complete, and stable semantics, and skeptical reasoning under stable semantics, and enumeration of extensions under preferred semantics. And again, we have 25 instances per each number of atoms, and here on the left of each cell we have the number of timeouts out of 25, and in the brackets the mean running time over all instances. And here we have fixed the proportion of atoms that are axioms to 1%. So from this you can see that naturally the hardness of solving these instances increases as you increase the number of atoms, and here in the bolded part are all the instances or the batches of instances where this approach solves a majority of the instances. So up to 3,000 sentences for most of these tasks, most of the instances are solved within the time limit. And this also shows that the hardness depends on the task. So enumeration under preferred semantics is clearly much harder than the other tasks, which again makes sense because the complexity of this task is also higher. To conclude, the algorithmic study of structured argumentation is an area where research is needed, and we have contributed this by providing complexity results for an instantiation of ASPIC Plus, and providing ASP encodings for this instantiation. And to provide these encodings, we define the semantics of ASPIC Plus directly on the argumentation theories, and skipping the AF construction step. And this is a first ASPIC Plus system that directly uses efficient declarative solvers to reasoning in ASPIC Plus. And our experimental evaluation shows that this approach scales quite well. In the future, we would like to extend this approach to different fragments of ASPIC Plus, probably most importantly to ASPIC Plus with preferences. And this is likely to have a higher complexity, so we'll need more complex algorithms. And also this can be extended to other argumentation formalisms and other declarative paradigms, such as proposition satisfiability. Thank you for listening.